Hello and welcome back to my channel. So this is the second problem on SFD and BMD. So in this question we have to draw the SFD and BMD, and also we have to locate the points of point of contraflexure. Okay, so the point of contraflexure is a point on the beam where the value of bending moment becomes 0. Okay, so we will be talking about this later in this video. So before that, the first thing we need to do is draw the free body diagram and to find out the reactions. So guys, in the previous video we saw that no reactions were given, only we had two supports and we had to resolve the supports into reactions. But in this video supports are not given directly, only reactions are given, so that's a good thing. Okay, so for calculating the reactions, we have to apply the equilibrium equations. So the very first thing that we can do is the summation of forces along the vertical direction will be 0. So what will be the forces? See, RC and RB, and it will be counterbalanced by the vertical forces in the downwards direction, that is 80. And what else? And see guys, in the entire beam, in this span, that is AC, in this section AC, we have an UDL, okay, whose value is 30 kilonewton per meter, right? So what will be the total value of this UDL? It will be the 30 multiplied with the span of the beam, that is 30 multiplied with 2, which will be 60. And what will be the point on which it will be acting? It will be acting on the point which is at the mid of the span, that is here, that is at 1 meter from A, right? So it will be acting somewhat here. Okay, so this will be also 60 kilonewtons. Okay guys, so it will be 80 plus 60 also, because it is also in the vertical direction and counterbalancing these both reactions, right? So RC plus RB will be 140, and both of these are unknown to us. So basically now we have to apply the moment equation. Okay, so you can take moment about this point, anywhere, right? So for my convenience, I will be considering point B, that is I will be taking moment about B, which will be equals to 0, of course, right? So I will be taking the anti-clockwise moment as positive, okay, and the clockwise moment as negative. Fine. So see, first let us consider this 80 kilonewton force. This will try to rotate the beam like this, that is in the anti-clockwise fashion. So it will be positive, so plus 80, and what will be the value of moment? Force multiplied with the perpendicular distance, that is 2 over here. Okay, so now 60, it will also try to rotate the beam in anti-clockwise, so it will be again plus 60 multiplied with the value of the perpendicular distance, that is, see, it is acting on the center of this UDL, right? So this much is 1, okay, this much is 3, and this much is 2. That will be 1 plus 3, 4, 6, right? 16 to 6. And the last but not the least, this one, that is RC. RC will try to rotate the beam in clockwise fashion, so it will be negative RC multiplied with this distance. So what will be the distance? 3 plus 2, that is 5, right, equals to 0. So if you calculate RC, it will come as, let me check please, it will come as 104 kilonewtons. So you put this value over here, you will get the value of RB also. So RB will be 140 minus 104, that is 36 kilonewton. So I'll do one thing, I'll just write the values over here. So RB is nothing but 36 kilonewtons, right, and RC is nothing but 104 kilonewtons, right? I hope this much is clear. So now basically what we have to do is to calculate the internal shear forces in all the sections. So in this particular problem, I will take the sections from right, okay, from right to left. Means I will treat point B as my origin, unlike the previous video where I treated point A, that is the leftmost point, as origin. I'll treat point B here as my origin, okay, just to give variations, okay, just to teach you the variations. Okay, fine. So first the section is DB, right? So I'll cut the section from here, say, so let it be my XX section, okay. Now, so just draw the section over here. So I'll write section DB, okay. So this is my section, this is my point B, where we have a reaction RB which is equals to 36 kilonewtons, and the section is let the section be from X distance from B, right? So what will be the value of forces? Okay guys, when we cut the section from right, we know that the shear force is upward and bending moment will be clockwise, right, like this. So this thing I have already taught in my first video where I taught the concepts of SFD and BMD. Okay, now what else? So this is my SX shear force, and this will be my MX, that is bending moment, okay. So now what will be the value of SX? So SX will be equals to, see, SX is up, so what will counterbalance this SX? Only there is 36. This value of force will be counterbalancing the value of SX, and you see that the SX and 36 is in the same direction, that is upwards. So basically it will be minus 36 kilonewtons, right? So note one thing guys, that in the value of SX we do not have any variable X. That means we can say that is across the section DB, that is across this section, this whole section, the value of shear force, the value of internal shear force will be same. That means we can write that the shear force will at B will be equals to the shear force at D, that is minus 36 kilonewton. Why it is so? Because it does not depend upon the variable X, right? So we can mark this. So let us first find out the bending moment, then we will mark this thing in the SFD and BMD, okay. So now the bending moment, okay. So MX will be equals to, see, this 36 kilonewton force, it will try to bend the beam like this, right? So this is known as sagging, okay. So what we can do, so MX will be equals to, sagging is positive, so 36, and what will be the value? This is the force. What will be the value of moment? So 36 multiplied with X, that is 36X. So in the equation of moment you can see that the value of bending moment depends upon X, right? So we have to find out individually what is the bending moment at B and D. So first let us find out at B. So the value of bending moment at B will be what? Will be from X distance, right? We are taking section from B, okay. So that means we are treating point B as our origin, okay. So what will be the value of B? If you just compress this beam, it will be, the value of X will be what? Will be 0. Then as you gradually expand the beam, the value of X will be increasing. So for moment about point B, the value of X will be 0, okay. So just put 0 over here, that is 36 multiplied with 0, it will give you 0 kilonewton meter. Similarly, what will be the value of moment at D? Sorry, this is D. This will be X equals to, see guys, this will be X equals to 2 x equals to 2 from the origin, right? Okay, so let us put x equals to 2, that is 36 multiplied with 2. This will give you 64 kilonewtons meter. Okay, sorry, this is not 64, that is 72 kilonewton meter. So let us put the values in the SFD and BMD. So let us first focus on this SFD. Okay, that is for SFD, shear force at B and D will be equal. So in this particular diagram, let us assume that this is my point where it is actually minus, so it will be in the below the baseline. Okay, so this is minus 36. Let us assume, let me write it in red, minus 36. And see guys, this does not depend upon the x. Okay, means we are going to have a constant value of SF, that is shear force. So it will be from B to D, the value of shear force will be constant. Okay, so this is done. Now let us plot the bending moments values. So at point B bending moment will be 0, this. Okay, and at point D the value of bending moment will be 72, means it will be somewhat here, right? So how do you join this? You join this by a straight line, because for the bending moment equation, that is this, you have a 1 degree polynomial, that is a linear polynomial. So you have to join this with a straight line. Done. So now let us consider section CD, which is at a distance of x from the origin. So I have drawn the section over here, x from the origin, and the distance between B and D is 2 meters, right? So first we need to solve for the shear forces, right? So see, Sx will be equals to, this Sx will be counterbalanced by two forces. Okay, sorry, here you have the reaction also, that is 36 kilonewton. So basically this Sx will be counterbalanced by two forces. One is this 80 kilonewton in the opposite direction, and one is in the same direction, that is 36 kilonewtons. Okay, so 80 minus 36 is how much? 44, right? 44 kilonewtons. So here also you can see the value of shear force does not vary across the section C and D, right? So therefore we can say the value of shear force at C and the value of shear force at D will be equal to 44 kilonewtons. So let us plot this in the SFD. Okay, that is, see, this is my point D and this is my point C, this is my B. So at D we will have 44, so 44 we will have somewhat here. Okay, and the value of shear force at C also will be 44 and will be independent of x. That means we are going to have a constant line, right? So let us join this. Okay, fine. Now let us calculate the moments. So mx is equals to first this one, 36 will try to sag the beam, right? So it will be positive multiplied with the distance, that is x, right? Minus 80. Why minus? Because it will try to, this force will try to hog the beam, right? So 80 into this distance. What is this distance? Total is x, this is 2, so it will be x minus 2. Do you have any other forces? No. So this is our equation. So if you simplify this, it will be minus 44x plus 160. Okay, so this is our moment equation. let us now find out the value of bending moment at D. So at D, the point D is 2 meter away from the origin. So bending moment at D will be equals to, when x equals to 2, so just put here x equals to 2, so it will be minus 44 multiplied by 2 plus 160, sorry, plus 160. So it will give you a value of let me check once, 72, yeah, 72 kilonewton meter. Okay, and on the other hand, if you try to calculate the value of bending moment at C, so at C, the point C basically will be from a distance of 2 plus 3, that is 5 from the origin. So here you have to put what, x equals to 5. Okay, so here you put minus 44 multiplied with 5 plus 160. So it will give you a value of minus 60 kilonewton meter. Okay, so the calculation of shear forces and bending moment is done for section CD. Now the last section, which is one of the important section, because you have the UDL over here, so this needs to be calculated. So let me just similarly just cut a section from here. I'm cutting the section is red. Okay, guys, before that we should plot this in the graph. Okay, so the so the value of the value of bending moment is to be plotted, right? So the value of bending moment at D is 72. Okay, so this is my C, this is my A, C, D, B. So the value of bending moment at D is 72. Means this was my 72, yeah, it will be here only. Okay, and the value of bending moment at C is how much? Is minus 60 kilonewton meter. So it will be somewhere here. Okay, so how would you join this? We will join this by what? A straight line. Why straight line? Again I am repeating, because in the moment equation you can see the polynomial is a linear or a 1 degree polynomial, so it will be joined with a straight line. Okay, let me use this scale, otherwise. Okay, so this is my minus 60. Okay, now let's come to the section AC. So I have taken this section in red. Now just let me draw the section. Okay, guys, this is the section. So let me just mark the points. This was my section B, where we had the force of how much? Of let me just check. It's 36, right? So we had a force of 36 over here at point B, right? At point D, we had a vertical force of how much? 80 kilonewtons, right? And finally we had a force of we had RC, that is 104 kilonewtons, and before RC we are having a UDL, right? We are having a UDL. So basically this section is from X distance from the origin, that is this point B. So let me just write, this is point C. Okay, so everything is done. I suppose everything is done. Just let me check. Yes, everything is done. So this is point D. Okay, now what? Now similarly you can give the direction of shear force and bending moment. Okay, so let's solve for shear force first. So shear force will be, see, this is balanced by 3 forces. This is basically counterbalanced by 3 forces. Firstly 80, because it is in the opposite side. Then we are having what? Then we are having 36. Just let me check, guys. I think I have done some mistake. Okay, no, it's okay, it's fine. Okay, so 80, and this is in the same direction, so it will be minus 104, and this is also in the same direction, so it will be minus 36, And what else, guys? What else? Now you need to like focus on this UDL part, right? So in the UDL, so basically in the UDL we had a unit force of 30 kilonewton per meter, right? We had a unit force 30 kilonewton per meter. Okay, but concentrate that this 30 kilonewton per meter is acting on the beam for a span of this much only. Means if you consider this section, so for this section the value, this UDL is acting on this part. Okay, so basically what will be the total force? What will be the total force due to this UDL on this part only? So it will be this 30 multiplied with this distance, right? Multiplied with distance will with this distance will give you the total force which is acting. And in which point will it act? It will act on the point which is on the middle of this span, that is somewhere here. Okay, so first we need to have this distance. So what will be distance? See guys, this is total, this is x, this much is how much? This much is 2, this much is 3. So it is basically x minus 2 minus 3, which will be 5, that is x minus 5. Mind it guys, we are basically multiplying a kind of distance to get the force. This is not moment. Okay, we are just getting the force due to UDL, because we know that in case of UDL we have to apply the unitary method to find out the total force. We are given only the unit forces, right? So we for finding the total force on the UDL, we have to multiply the force with the distance. So this is it. Okay, so one more thing we had, that is this one, this one, which is okay, this will be 30, right? This is not 36, this is 30, I'm sorry, this is 30 multiplied with this distance, and this 36, that is minus 36. Okay, now if you solve this, you will be getting somewhat like this: 30 x minus 5 minus 60, right? So now see in this value of shear force, this shear force is basically dependent on the value of x. Okay, so we have to individually find out the value of shear force at section at A and C. So this is basically section AC. I have not written the section, sorry. This is basically section AC we are considering. So first at section C. Okay, so first let us find the value of shear force at C. So C is what will be the value, what will be the distance from the origin at section C? So it will be 2 plus 3, that is 5, right? So for finding out the value of shear force at C, we have to take x equals to 5. So you just put the value here, that is 30, 5 minus 5 minus 60. So it will be giving you minus 60 kilonewtons. Okay, very simple. Okay, similarly at the value of the value of shear force at A, this will be the value of x will be 2 plus 3, 5 plus 2, 7, right? The value of x will be 7 at A. So just put the value over here, 7 minus 5, sorry, minus 60. So this will give you 2 multiplied with 30, 60, this will give you 0. So the value of shear force at A is 0. So let us plot the points, guys. So the value of shear force at C, that is, this is my C, right? So this was my how much? This was my 44, right? So the value of shear force at C means minus 60, mind it. So it will be below the baseline. So here, right? Okay. So let us join this. Fine. Okay. So now the value of shear force at A is 0. So again, A is 0 means it will be here. So let me write here minus 60, guys. So just join this with straight line also. Why straight line? Because we are having a 1 degree polynomial. As simple as that. Okay, now let's move on to the bending moments. Okay, here the bending moments, that is mx, it will be equals to first this 36 multiplied with this distance, that is x. So this 36 kilonewton will try to sag the beam, so basically positive. Okay, then this 80, it will be minus because it will try to hog the beam, right? So 80 multiplied with this distance, what is this distance? Total is x, right? And this much is 2, so you have to subtract this 2, so it will be x minus 2, right? Then this 104 kilonewton force, it will also try to sag the beam, so it will be again positive. 104 multiplied with this distance, so what is this distance? Total is x minus this much, that is 5, so x minus 5. And finally guys, we have this force, this will try to hog the beam again, so it will be minus, right? So see guys, now what is the magnitude of this force? The magnitude of this force is 30 multiplied with this distance, right? This distance. Okay, so this was x minus 5 as we did earlier, right? Now see one thing guys, this is the magnitude of the force. Okay, now you have to calculate the moment. This means we have to multiply this much distance. Now we need to multiply this much distance in order to get the moment. So what is this much distance? See, what is this much? This is basically nothing but the half of this, right? What is this? This much is how much? This much is x minus 5. So what will be this much? Is this much will be x minus 5 by 2. Simple, right? So if you just calculate this, you will get a simplified equation. I'm just doing it directly guys. So you need the value of bending moment at C. So at C, what will be the value of x? The value of x will be 2 plus 3, that is 5 from the origin. So if you just put the value of x in this equation, x equals to 5 in this equation, you will get mc minus 60 kilonewton meter. On the other hand, if you want to find the value of bending moment at A, so it will be at a distance of 7, I guess. 2 plus 3 4 5 plus it will be 7. Okay, so it will be x equals to 7. Okay, I hope this much is clear, right? At point A, this will be equals to x equals to 7, right? 2 plus 3 5 plus 2 7. Okay, so this will be how much? If you put x equals to 7, you will get 0 kilonewton meters. So just put the value of mc and ma in the shear bending moment diagram. So mc will be minus 60. So this is my mc minus 60, and what will be the value of ma? It is 0. Now guys, one thing to note very carefully, that now how do we join this line? So if you check the bending moment equation, that is this is what kind of polynomial is this? This is basically 2-degree polynomial. See, if you solve this, I have not solved this basically, but if you solve this, you will get a 2-degree polynomial, right? Due to this term. Okay, you'll get a quadratic polynomial. So basically the graphs of quadratic polynomial are always parabolic. So you will join these 2 points not by a straight line but with a parabola. Okay, so this is 0. Okay, so this is how you draw the shear force and bending moment diagrams. So you can just give positive, and this one is negative shear forces, and this much is negative shear forces, and this much is positive shear force. So our first part of the problem, that is the drawing of SFD and BMD, is done. Now we have to locate the point of contraflexure. So I have already told in the beginning of the video, that is a point of contraflexure is that point where on the beam where the value of bending moment becomes 0. So you can find this out from the bending moment diagram. So if you carefully see, at this point the value of bending moment is becoming 0, right? So basically what you have to do is you have to just a second, let me just draw the line over here. You just have to locate the point from the origin, right? Means what? Means we have to calculate this distance from the origin, right? Because we don't have any other way to locate this point, so we can only locate this point with respect to the origin. So we have to find this distance. So how do we do that? So before that, please do give it a watch that this point of contraflexure, this is basically nothing but the point of contraflexure. Let me just write it, guys. Point of contraflexure. Okay, this is the point of contraflexure. Okay, and this point lies in the section CD. Okay, this lies in the section CD. So for calculating this point, we will consider the bending moment equation at section CD. So where is the equation that I wrote? Okay, this is my section CD, and this is the bending moment equation for section CD. So for finding the value of x, what we will do is we will just equate this, because at the point of contraflexure. So let me write at the point of contraflexure, the bending moment becomes 0, right? So basically to find the value of x, we can just equate this equation with 0. Is as simple as that. Okay, so if you just now if you calculate the value of x, so x will come to you as, let me just check, I have already done the calculations. So x will come to as 3.64 how much meters, right? So now we can say that basically this point of contraflexure is at a distance of 3.64 from the origin, that is my point B. So I hope this video is very much clear to you. So many more problems are coming, so make sure you do please like my video, share this video and subscribe to my channel. So thanks for today, see you next time.